So if I have two distinct planes, either these planes, they're either parallel, or if they intersect, then they're going to intersect in a line. So if you want to see why this is true, maybe take two sheets of paper and show them intersecting each other, and you'll see that what they share, what they have in common is a line. So if these two lines intersect, if they intersect, you can determine the angle, which would be between 0 and pi over 2 between them. And how would you do that? You would find that angle using the angle between their normal vectors. So you would have cosine of theta if n1 is going to be the normal vector for the first plane and n2 is going to be the normal vector for the second one. Then this would be our formula for the angle between those normal vectors, and then it'll also be used for the angle between the planes. So then we can talk about two planes with normal vectors, n1 and n2 are, well, they're going to be perpendicular when n1 dot n2 is 0, and they're going to be parallel when one of the normal vectors is a scalar multiple of the other one. So let's look at the following example. What I want you to do is find the angle between the two planes x minus 2y plus z equals 0 and 2x plus 3y minus 2z equals 0. Then what I want you to do is find parametric equations of their line of intersection. So let's look at our first plane equation, and I need a normal vector for that first plane. So one way you can get a normal vector is just read off the coefficients of x, y, and z. So here it would be 1, -2, 1. So that'll be a normal vector for the first plane. Now if I look at the second plane and I want a normal vector for that, again, just read off your coefficients of x, y, and z, 2, 3, and -2. So now I'm going to use my formula. Cosine of theta is this dot product, the absolute value of that, over the magnitude of n1 and the magnitude of n2. So if you take this dot product, you would get 2 minus 6 minus 2. The magnitude of n1 would be the square root of 6. The magnitude of n2 would be the square root of 17. So I'm getting the absolute value of negative 6, so positive 6 over the square root of 102. And that's what cosine of theta is, but I really need to know what theta is. So you're going to have to use the inverse trig function, inverse cosine. And if you pull out a calculator, you'll see that theta is approximately 53.55 degrees. If you need a rounded version of that. So if I look back at the problem, let's look back, find the angle between the planes. I've done that, but now I need to do the second part. I need to find parametric equations of the line of intersection. So let's do that. First thing I'm going to do is I'm going to copy down my two equations of my plane. So it's x minus 2y plus z equals 0, and 2x plus 3y minus 2z is 0. And what I want to do is I want to eliminate one of my variables. So I'm going to multiply my first equation. I'm going to multiply that by negative 2. So I'll get negative 2x plus 4y minus 2z equals 0. And then I'm just going to leave the second equation alone. And now if I add these two together, my two x terms cancel. So I'm left with 7y minus 4z equals 0. And you can solve for one of the variables. I'm going to solve for y here. Y would be 4z over 7. So then what you're going to do is take this and plug it into either one of your plane equations. So I'm going to plug it into the first one there. And I'm going to get that x minus 2 4z over 7 plus z equals 0. And you're going to solve for x. So I will get x minus z over 7 equals 0. X equals z over 7. So now what I'm going to do is I'm going to replace, I'm going to use my variable t, which remember I need for my parametric equations. I'm going to use t as z over 7 to get my parametric equation. So from here, I'll get x equals t, and y, if you look back at y, it was 4 z over 7, so it'll be 4 times t. And if I solve for z in this equation here, it would be 7t. So here's my set of parametric equations for the line of intersection here. And I do want to note that you can also get these direction numbers, these coefficients of t, you can get these direction numbers from the cross product of n1 and n2. I'm not going to show that here, but you could get these coefficients in front of these t's here, these coefficients here from this cross product here.